My name is Gabriel Rentap with metric number 74883, and I'll be representing my group to talk about the study report, which is the performance analysis of Yanggun's steam power plant located at Sungai Bau, Sarawak, and we're going to study the different work production.
First, I'm going to explain abstract. So the abstract for our report is a steam power plant is a thermal power plant that utilizes the Rankine cycle to transform electricity from heat energy. This technical report is to create a complete model for the chemical and physical processes that occur in the steam boiler at Yanggun SDN Berhad steam power plant. This steam power plant utilized the Rankine cycle via the usage of DWSIM simulator. So this simulation for 18 kilowatt power produced from the turbine is explained in the methodology part. Furthermore, in the methodology part, we also include all the formulas, parameter and consideration that are needed to produce 18 kilowatt power from the turbine. To fulfill the current demand for the work, which is to produce 350% work demand equal to 93 kilowatt power that produced from the turbine, our solution is to reduce the pressure of the water feed. So the theory and the result of the modification of the cycle are briefly discussed in the result and discussion part. That will be explained after this.
For introduction in this study report, we're going to talk about at least 4 keywords, and we're going to define them one by one. The first one is power plant. Now, what is a power plant? Power plant is a machine that produces and transfers a mechanical or electrical energy, which requires a generator. The power plant we're going to talk about in this study report is the power plant from Yanggun Sdn Bhd, which is located at Sungai Bau, Sarawak. Now, moving on to the Rankine cycle. Rankine cycle is used in electrical production, and it's a type of heat engine that is influenced by vapor power cycle, and its energy transfer medium is water. Now, the next one is Bhd'S. Now, what is a Bhd'S? Bhd'S is a non-proprietary software that serves as sequential modular steady-state modeler for chemical processes. In short, this is a type of software that allows you to create chemical or at least simulate a chemical processes digitally, and is invented by Daniel Medeiros and is often used by engineers worldwide. When it means being non-proprietary, it means as a free software. So the other one is steam boilers, which is a sealed containers constructed with steel that functions to boil water that is fed to it using fuel combustion in order to produce steam. So what we're going to talk about in this report is that we're going to talk about Yanggun Sdn Bhd power plant, which will be using Rankine cycle. We'll focus on that only. And we're talking about Rankine cycle, we're going to talk about steam boilers, but we'll also talk about other unit of operations, which is the turbine, the pump, and the condenser. And we're going to recreate all the chemical processes of the Rankine cycle inside the steam boilers using the Bhd'S simulator. Now, the aim and objectives of this study report, well, first of all, the aim is to improve the Rankine system by modeling and then understanding it so that you can understand it and then improve chemical processes via Bhd'S to simulate the whole chemical processes that happen. The other objective is to create a complete model for the chemical and physical processes that happens during Rankine cycle plant using the Bhd'S simulator. The other objective is to present alterations or modification for Rankine cycle plant in each of its unit of operation like steam boilers, turbines, pumps, and its condensers to achieve the elevated work efficiency requested by the company, which is 350%.
Next, I will explain the methodology part. So first, I will explain all the formula used to get 18 kilowatt work from the turbine. So firstly, the Rankine cycle, which is the cycle that been used in our power plant, in our steam power plant. To calculate the efficiency, we use the formula efficiency equal to the W from the generator, which is work from the generator minus the work from the pump by the heat input. So the second formula is the efficiency formula, which is the heat input minus the heat out minus work from the pump divided by heat input. In TS diagram, which is the diagram that we will use when we try to improve the work done by 350%. So the heat input described as the Q input, which is the heat input, equal to the integral of T steam, which is the temperature of water in the condenser, in order to use all the formula that I have been mentioned before, we need to find the work done by the pump first. So the work done by the pump equal to the integral of pressure of water to the volume before compression, which is the VB, minus the volume after compression, VC. Next, to calculate the turbine work, the turbine work equal to the mass flow multiplied by the inlet enthalpy minus outlet enthalpy. And then we will obtain the turbine work, which is 18 kilowatt work that we need for the turbine to produce at normal operation. Since the volume of the water is smaller than the volume of the steam, the pump work can almost be ignored in the calculation. So we no need to calculate the pump work. And to calculate the efficiency, we use the following formula, which is the integral of T steam minus the integral of T condenser divided by the integral of T steam. To obtain the work efficiency of the power plant, which is the steam power plant of Yanggun sendirian Berhad, we use the equation below, which is the efficiency, the work efficiency equal to the WX, which is the actual work, divided by WREF, which is the isentropic work produced, multiplied by 100%. Next, I will explain the thermodynamic model that our group been used to stimulate the process that occur in Yanggun steam power plant normal operation. So the basic equipment to operate Rankine cycle are pumps, water boiler, turbine, condenser, and valve. The thermal efficiency is highly dependent to efficiency of the equipment, which are boiler, turbine, and condenser. Any changes in inlet or outlet temperature will affect the isentropic and thermal efficiency of the turbine. In order to obtain 18 kilowatt work produced from the turbine, we design our stimulation using the above information and assumption. So there are 5 assumptions have been made for our simulation, which is our design. So firstly, the molar flow rate of water we set up equal to the 0.75 kilogram per second. Next, the temperature of water feed equal to 298.15 Kelvin. The pressure of water feed was set up equal to 486,754 Pascal. And next, the pipe and equipment are in perfect condition, which is no leaking happen between them. And lastly, there is no pressure drop in the boiler and the condenser. So the table 1 show the work efficiency given for the every equipment, which is the every unit operation used in our stimulation, in our, or as I can say, in our normal operation ranking cycle. So first, the equipment is pump. So the work efficiency for the pump is 85%, boiler 95%, turbine 85%, and condenser 98.5%. Figure 1 shows the simulation of process occur in steam power plant for 18 kilowatts from turbine. So this simulation been created in DWSIM software. So this is the simulation of process for our. So as we can see here, we have 1, 3, 4 unit operation and some stuff here to ensure the stream not going back to the previous unit operation. Next, we move on to the steam parameter. All the parameters be used in this simulation. Given a fixed set of initial steam parameter as shown in figure 2, by lowering the final steam parameter, create a larger temperature difference between the temperature steam and temperature of the condenser, thus lifting the theoretical efficiency threshold for the thermal power plant. Changes in pressure, temperature and flow rate at inlet or outlet condition will affect both the isentropic and the thermal efficiency of the turbine. So as we can see in the figure 3, that shows the energy flow by the turbine work, pump, condenser and boiler, we has successful obtained the 18 kilowatt work from the turbine by using the assumption that I mentioned before in the previous part. Next, I will explain the modification that our group been choose to get the 315% work demand from the turbine. So figure 4 showed the effect of lowering the condenser pressure on the ideal ranking cycle. As we can see on the graph, by decreasing the pressure of the condenser, the area enclosed by the cycle of the TS diagram, as shown in figure 4, will expand to show the increase in net work. As a result, the thermal efficiency of the cycle will improve. In other words, the work that produced from the turbine also increase. Next, for our group to know how much the work produced increased significantly to 315% of the system normal operation, we use the equation below, which is the W work for 315% equal to W normal, which is the turbine work at system normal operation, which is 18 kilowatt, multiply by 3.5, which is 315%, divide by 100%. Therefore, we can summarize that wherein the new operation, the work produced will be 93 kilowatt power or work produced from the turbine. In the new operation that we will be modified and we will be explained in the result and discussion part.
Moving on to the result and discussion, we decided to use the same design as the normal operation. We only modify the parameters of the water feed. So basically, we can see that the assumptions for 350% for work demand are the molar flow rate of water equals to 0.75 kilogram per second. The temperature of water feed equals to 298.15 Kelvin. The pressure of water feed, which is 112,790 Pascal. The pipes and equipment are in perfect condition, means no leaking and etc. There is no pressure drop in the boiler and condenser. So as you can see from the assumption, uh, most of them are the same as the normal operation except the pressure of water feed, which is it decreases from 486,000 Pascal to 112,000 Pascal. Moving on to the parameters used in steam power plants after 350% of work demand. As we can see from the table, the temperature throughout the cycle is the same as the normal operation, which is 298.15 Kelvin, 456.34 Kelvin, 298.15 Kelvin, 298.15 Kelvin, and 500 Kelvin. For the pressure, we can see that uh, it differs from the normal operation, which it reduces from 480,000 of Pascal to 112,000 of Pascal. So we can see there is significant changes of pressure throughout the cycle, going through from water fed, turbine outlet, pump outlet, condenser, and the boiler. For the mass flow and molar flow rate, it is the same throughout the cycle, which is 0.75 kilogram per second and 41.63 mole per second. Moving on to the energy flow by turbine work, pump, condenser, and boiler after 350% of work demand. So the turbine work increases up to 63 kilowatt from 18 kilowatt, which is what we want for 350% work demand. The pump energy is 0.063 kilowatt. The condenser is 2083.65 kilowatt, same as the boiler energy. Moving on to the temperature and pressure at turbine outlet. As you can see from the graph, the temperature and pressure at turbine outlet for 350% work demand is lower than normal operation. For the specific enthalpy and power variations, we can see that the 350% work demand has a larger enthalpy difference than normal operation. This is because the power generated by the 350% work demand is larger than normal operation by 350%, which means it has 63 kilowatt power generated. Meanwhile, the normal operation has a 18 kilowatt power generated, which sums up the difference between the enthalpy and the power variations. By using the equation 3.5, we can calculate the work produced by the steam plant respectively for normal operation and 350% work demand. The amount of work produced is obtained from the calculation using the parameters of the models. For normal operation, 18 kW of work produced is obtained. For 350% of work demand, 63 kW of work produced is obtained. Moving on to the thermal efficiency of power plant. The thermal efficiency of power plant of normal operation and 350% work demand was obtained in the table. For normal operation, the thermal efficiency is 0.4, which is the same as the 350% work demand. So the table shows that the efficiency for 350% work demand is the same as normal operation. Thus, the unit electricity and the economic criteria does not change, which does not benefit for Yanggun sendirian berhad in the long term. The system equipment will operate on design conditions that less damage them. Meanwhile, the energy invested for normal operation and 350% work demand are shown. For the normal operation, it is found that energy invested is 0.85%. For 350% work demand, it is shown that the energy invested is 3.02%. So as we can see from the table, 350% of work demand has a higher energy invested compared to normal operation. Both conditions have low energy invested. So to maximize the energy invested and thermal efficiency, we can run the system at a higher temperature and use more quality equipment for longevity. So moving on to the comparison between actual work efficiency and the given work efficiency for both conditions. Firstly, I'm going to talk about the first condition, which is normal operation, which is shown in the table above. So the given work efficiency is 85% for the pump, 95% for the boiler, 85% for the turbine, and 98.5% for the condenser. Now I'm going to explain the actual work efficiency for normal operation. Firstly, the pump is 84%, the boiler is 93.4%, the turbine is 83.4%, and lastly the condenser is 97.6%. Moving on to the next condition, which is 350% of work demand. As we can see that from the table below, the actual work efficiency for the pump is 83.2%, for the boiler is 94.5%, the turbine is 83.2%, and lastly, for the condenser, it is 97.3%. So as we can sum up between both of the tables, the actual work efficiency for each equipment for normal operation is nearer to the given work value. This is because the increase of work demand stresses out each of the equipment leads to lower work efficiencies.
The conclusion for this study report is that the two objectives have been accomplished. The first objective is to create a complete model for the chemical and physical processes that occurs in Rankine cycle plant. And this model is created using the Sem simulator, and it can be seen in figure 3.1. And the subsequent results for each of the unit operation, like the steam boilers, turbines, condenser, and the pump, can be seen in figure 3.2 and 3.3. This for the basic requirements for the normal operation. Now the second objective, the cycle alterations, which mean the Rankine cycle plant modifications, are proposed to achieve the the new targeted work efficiency, which is 350%, is accomplished, and the proposed modifications can be seen in slides 13 and 16.